Hi, everyone. Welcome to the afternoon part of the second day of ZuriHack. We're going to have the Datatype-generic programming track. So Andres is probably a familiar face if you've been to ZuriHack before. He's one of the partners at WelpTyped, I think the oldest continuously operating Haskell consultancy. And since recently, he's also the chair of the Haskell Foundation board. Yeah, take it away.
Thank you very much, Jasper. Yes, so a couple of things up front. So so this is mostly going to be live coding. So that's why there is a small file in the repository. So if you want to try to do the same things I'm doing or similar things I'm doing, you have a chance to clone that repository and basically try to see whether Cabal build or Cabal REPL or whatnot works. And hopefully that will give you sort of the same starting point that I have. The plan today is to do data-type generic programming and mostly using a library that I've co-authored, namely Generics SOP. I have been giving other talks about generic programming before, including at ZuriHack. I have often observed that I have afterwards had the feeling that I have been perhaps doing an okay job in motivating what generic programming is all about and perhaps even building up some of the ideas, but then had to stop due to lack of time before I had written any actually substantial generic function. And I mean, that is a problem with a limited amount of time because there is quite a bit of explaining to do and theory to do. And it may happen again, but I want to start the other way around. I want to start with showing what the goal is and working from the goal through the necessary concepts and hopefully thereby ensure that at the end we have been writing at least one not completely trivial generic function together. Perhaps I would like to get a little bit of an overview. Who of you have an idea of what data-type generic programming is? Okay, that is more than half. Who of you have been using Generics SOP before? That is not that many, that's good. Because you might be bored otherwise. Perhaps also something like, who of you know what GADTs are? Who of you know what type families are? Okay, well, that's not too bad, actually. Okay. In any case, I would like to encourage you to keep this interactive. I really like to be interrupted. Please ask questions the moment you have them. Don't wait until any later point. I think, I'm not sure whether Jasper is going to walk around with a microphone or otherwise. I can also repeat questions if that is necessary, but basically, yeah, don't hesitate to just ask. Okay? Yeah, you have a question. Yeah.
Maybe you're going to answer this anyway, but I'm wondering. I know that there are several different generics frameworks. So why Generics SOP as opposed to GHC generics?
Okay. So the question is why Generics SOP rather than any of the 1,000 other generic programming libraries that are around, including GHC generics. Yeah, do I want to answer this right now or do I want to answer this later? Perhaps, why not? So let's very briefly say, let me start with what the goal is, and then I'll answer your question. So the goal, at least in the first part, if we have time in the end, there is a secondary goal, but I will reveal that then. The goal in the first part is to pick a classic example where generic programming can be used. And I decided to basically redo something that is already done in the library, but to pick the serialize and the Seaborg libraries, which are a way to serialize data types. And serialization is a typical application area of data-type generic programming, because what you primarily care about is that if you serialize some data and then you deserialize it later, that you get back what you have serialized, but you don't really care very much about how exactly it is going to be serialized, as long as it works with a reasonable amount of effort. So you would like to have a way to say, if I have an arbitrary Haskell data type, give me just some magic serialization function and give me some magic compatible deserialization function. And I would like not to have to do work for it, right? So, so here's an example. This is sort of a lambda calculus-inspired expression data type, but it's really just an example data type that you could have, right? And if you want to manually serialize that data type using the serialized library, which is based on Seaborg, you have to define an instance for the serialized class, and you have to define two methods, encode and decode, which we are setting to encode expression and decode expression. And this is the kind of code that you have to write. For encode, you basically match on the constructor, and then you're creating something which is called a Seaborg list. And the Seaborg list is essentially it contains a tag and then a payload. And the tag is indicating which constructor you're in. And the payload is basically all the serialized fields of the constructor. So if you look at the encode word there, encode word 012 is the tag, because you have three constructors, so you number them 0, 1, and 2. And then the rest is just recursive calls to encode or encode expression, depending on what the arguments of the constructor are. And then in the very beginning, you basically wrap it all up in a list, and because the list consists of the tag and the payload fields, it's always one more than you expect. So var has one argument, but then the list together with the tag is of length 2, and app has 2 arguments, but then together with the tag it's of length 3, and lambda as well. Okay? So that's what you would have to write manually for encoding expressions, and what you would have to write manually for decoding expressions is something like this. So you would first decode the list length, and perhaps we should actually check that the list length is not 0 if we want to be careful, right? But that's a sort of a relatively small change compared to this. Then you decode the word, which should in principle always be there, which tells you which constructor it is. And then you match on primarily the tag. The matching on the length is really also just a robustness check, right? Primarily the tag, in order to see what you actually want to decode. And then you do recursive calls to decode and decode expression, and then you wrap it up in the right constructor, and otherwise you fail, right? So it's all straightforward, mechanically following the structure of the data type somehow, but it's not fun to write, right? It's not something that takes creativity, it's just work, and if you later modify the data type, you have to tweak all these functions. So this is why you want generic programming in the first place. So now let me try to answer the question about which generic programming library. I mean, obviously, in this particular case, and in many cases, you have one generic implementation already, right? So if you are actually going to use the serialized library, it comes with this generic functionality. We could just write deriving any class. I'm explicit about the deriving strategy here, but you could also actually just write that without the strategy, without stock and any class. You have to derive the GHC generic class, that is also stock. And then you can derive, as GHC. Let me do that one here, as GHC. And now, okay, now it's complaining about the duplicate instances because I've already given an instance declaration. So, but I could do this, right, and it would just work, right? So, that's fine. I mean, so that's using the already given one. So the first answer is like, okay, if you already can rely on functionality that you have, then it doesn't really matter which library has been used. You can just enjoy enjoy what you're doing. You don't have to rewrite it just out of principle like I'm doing here for illustration purposes. But if you want to write something new, yeah, then there is an option. And so the reason I like Generics SOP is because it feels like functional programming. It's based on the idea that you are sort of looking at the big picture, you're decomposing it, the functionality that you want to implement into multiple reusable steps, that you're using higher order functions in order to unleash a lot of power, and it's just fun, right? Whereas if you, for example, write stuff using GHC generics, you have to define sort of many different class instances for cryptically named data types, for which I'm partially responsible as well. I'm very sorry. And basically, yeah, but it feels like you're writing sort of a big case statement, right? It's a little bit like when I teach people Haskell on the first day, and there's nothing wrong with that. I say, like, if you define a function over a data type, then look at the constructors of the data type, do a pattern match on that data type, like create a case for every single constructor, and then think about how to implement every single constructor. And in the beginning, that is good, that is systematic, that is structured. But over time, the true power of functional programming is that you can say, oh, it's just a filter of a map, right? And that's where the fun starts, right? And that is basically Generics SOP is giving you a way of doing that on the type level. It's all more complicated because it involves type level stuff, but it's still the same principles, right? It's higher order functions that you can compose together, and I think that is quite nice. There is also a disadvantage, though, and I would like to basically, at least perhaps at the very, very end of time permits, just not talk about efficiency today at all. Both. The question was whether compile time or runtime efficiency. So Generics SOP is particularly bad in both compile time and runtime efficiency. I have very concrete plans of how to address that, but in general, generic programming is bad in compile time efficiency, just to summarize it in one sentence, because it decomposes data types, like a data type construct such as this, into some way of repeatedly applying product and sum constructors, right? So there is like a concept of a choice between different constructors and a concept of sequencing different fields of a constructor. And you're typically going to have multiple such choice constructions and multiple product construction. Because GHC internally uses an explicitly typed core language, that leads to the fact that the types of the constituent expressions or type structure are repeated over and over again, which generally leads to something like a quadratically sized core program for a linearly sized input program. And that drags down compile time performance. And the runtime performance is bad because it introduces overhead. And sometimes GHC can optimize that away, but GHC generics is actually relatively okay to optimize just by inlining everything, which further drags down compile time performance, but restores some of the runtime performance. Because everything is higher order recursive, Generics SOP is not so nice to optimize at runtime by inlining everything away, because GHC will just refuse to inline recursive functions with good reason. But yeah, there are some tricks. But let's leave it at that for now and perhaps revisit the question at the end. Okay. Any further questions right now? Yes. Yeah, so okay, the question was, what is the stock and the any class and deriving? Classically, GHC has just one way of deriving things. That is sort of like or classically Haskell has just one way of deriving things. If you look at the Haskell report, it'll say there is a fixed number of classes you can use deriving on. That is what is reflected, like if you want to spell it out using a so-called deriving strategy by writing deriving stock. That is sort of the way of deriving that is defined in the Haskell report. That basically says, rely on magic that is built into the compiler for that particular class. It's only applicable to classes that the compiler knows about up front. And then there are various other ways of deriving things. The probably longest, like the one that has the most history compared to the others is new type deriving, where you can say a new type is essentially a wrapper around an already existing type, but it has exactly the same representation as the wrapped type, and therefore all the class instances you have on the underlying type you can just magically lift to the outer type, so that if you want to if you want to make it clear that you're using that deriving strategy, you can write deriving new type. Because sometimes you have two different ways, right? That was the original motivation for introducing these explicit strategies. Like if you have a new type and you want to derive show for it, for example, right? You can decide whether you want to have the stock derived show for the new type, which includes the constructor name and the serialized representation, or whether you want the new type derived show instance, which does not, because it just uses the underlying. And sort of disambiguation was the original motivation for allowing to specify the strategy. And then any class is sort of motivated by generic programming that basically says, just use the defaults or generic defaults that are specified in the class definition for everything. So if a class definition has either a normal default or a generic default for every single method, then just fill the definition in by those. And then there is one more, which is deriving via, which we may actually see today later on, okay? Okay, good. So how do we go about this? So, I mean, perhaps let's look at an example. So this is an example expression. This is a call of serialized to the expression. So you get some kind of byte string that looks weird because it's all binary. And but the important thing is that if I deserialize the serialized expression, then it succeeds and gives me back the original expression. So we want to keep that. But what we would like to write is sort of generic versions of encode expression and decode expression. And what are the concepts that we need, right? So we need something like mapping constructors to numbers, right? So we need something like if it's of the first constructor, we would like the tag to be 0. If it's of the second constructor, we would like the tag to be 1. We need something like counting the number of arguments of a constructor in order to determine the list length. And we need some mechanism to just like recursively call across the board the encode and the decode function. Right, so these are all different things that we need. So which one do you want to start with? I'm actually a little bit undecided. So encoding is easier, and decoding is harder, but I'm undecided what's better to start with. Who's in favor of starting with the easier thing? Okay, well that's clear. I don't have to ask then. All right. So let's see. The basic idea of a generics SOP is that you have a function that's called from, and if you, I mean, first of all, you need an instance of a class that is called generic, similarly to the GHC generic that we already have. So there is a way that we can, this is sort of magic that I won't really explain today. that you basically need an SOP generic class as well defined. And the reason that this one is any class and not stock is that GHC knows about GHC generic, whereas the SOP version of the generic class is something that GHC does not know about, so it has to be implemented via other mechanisms. But the first thing you need is you need an instance of sort of the SOP version of the generic class. So this one is, I can also perhaps highlight that this one is the SOP version of the generic class, and right up here, generics SOP as SOP, right, just so that it doesn't look a little bit more symmetric here. So if we have the instance of that class, then if we write something like, let's do it perhaps here. If we write something like from var x, right, and evaluate that, we get what I call a generic representation of this original value. And this is actually not so bad. I mean, even if it looks like it has a little bit of noise, but the SOP is just a marker, right? You can disregard it. All these representations always have SOP in the beginning. The Z is an encoding of a number, right? Of a piano-style natural number. You can read Z as 0. And that's nice because we need such a number anyway, right? So we need a tag for the constructor in the end. So that's because var is the first constructor in the data type. We get such a number encoding already, and the rest is a list, essentially. Think about it as a list, and the list contains all the arguments of the constructor, and the var constructor has one argument, so there is one element in the list, and this colon star is essentially the cons operator of this particular list type, and then the x is also marked with an I, but let's disregard the I for now as well. So basically we have a number and a list, right? That's the important ingredients of the generic representation. If I do the same thing for app, and perhaps do app var x, var y, or something like that, then I get another representation, which uses successor of 0 as the number, right? So that's 1, and then has a list with 2 elements in it. And the representation is not recursive. So all the arguments are just left alone, right? Even though the arguments in the case of the app constructor are expressions again, they're not being touched. There's just var x and var y which reoccurs. Yeah, there is a question.
So we seem to have lost the constructor names. Is there a way to recover?
Right, so the question is, we seem to have lost the constructor names. Is there a way to recover them? That's a very good question, yes. Like the answer to your observation is yes, and the answer to your question is yes. So we have lost them, and at first that is actually a good thing, because in many cases we don't care about the constructor names. Types are often sort of identified by structure, and in particular for serialization, we don't really care about the constructor names. We only care about the numbers. Like the constructor names do not appear in encode expression either. But if we need them, yes, we can recover them. There is a way that we can recover them, and ideally I'll have time in the end to show that. But yeah, that's a very important observation. Okay, so the good thing of having this representation that is sort of a number and a list is that we can now sort of generically operate over this, right? So we can use, and that's where the higher order functions that I talked about come in. We can, for example, like traverse the list and count how many elements are in there, right? In order to determine something like how long the list length that we have to encode for the serialization representation needs to be. We can transform this piano-style numeric representation into an actual number in order to get the tag. And we can also do some sort of mapping over the list and effectively also the number part, but in particular the list, in order to say, well, for all the things that are in the list, we actually want to recursively apply encode. Right? So these are all sorts of operations that we would like to do, and that's exactly sort of what we, in principle, can do. So let's perhaps write a simple part of this first. Let me see what we want to start with. Perhaps let's say if we want to just count the number of elements in such a list, right? I mean, how do we do that? So for that we have to, let me call that count arguments or something like that. For that we have to know what is the type of this list, right? And the type of this list is, and that's why Generics SOP is called SOP, because SOP stands for sum of products. And that's because it's built on like sums and products. And these lists are products, right? They're sort of heterogeneous lists which have sort of type level information attached to them, but that's what's being called a product in Generics SOP. And these sums with an argument, basically, the numbers with an argument are essentially sums. They're sum because you make a choice between a certain number of different choices, right? If you have 5 different things you can pick, then you can identify the choices by saying, I want the first, the second, the third, the fourth, and so forth, right? I mean, so basically the number is an instance of the sum type, and the list is an instance of the product type. So if we just want to count the arguments, we can say, if we have a product, and so the products are called NP for n-ary product. Again, I'm not good at naming, but the motivation is that product is long, and you have sums of products and so on, and then the types get very long, and I don't like that. But that's the point. And we don't really care what the product is parameterized by. I'll explain more about what the f and the xs is. And we basically want to just count the length of the product. Right. Now there are multiple ways of like perhaps qualities of defining this, and again you can define this in a sort of very straightforward pattern matching, explicitly recursive style. So that is one option. So you can do something like this. Right, and then we have to enable the GADT's language extension. Okay. So that's one option. Now we have defined not necessarily great, but we have defined a working length function on a product. It's just like you could define a length function on lists, right? For the empty list is 0, and otherwise you add 1 to the result of the recursive call. But even for something like this, if you really wanted to, here I'm not really necessarily going to say that that's the better way, but I already want to kind of show the different styles you can adopt. What you could also do is you can say, okay, so this is a heterogeneous list, right? The product is a heterogeneous list. And the reason I cannot just use the normal length function on lists that I already have is that the normal length function on lists only works on homogeneous lists. But perhaps I can turn the heterogeneous list into a homogeneous list, because I don't really care for just determining the length. I don't really care what's in the list. So I can change the elements. And changing the elements is a map, right? So I can map over this product. So let me call this P for product. So I can map NP over the product, and then I still have to do something afterwards. Why is this one complain? Okay. Yes. Sooner or later I have to describe what this means. I'll just add it for now. There is an extra class constraint. But apart from that, I can basically just do this, okay? And so and what do I do in order to map? Well, basically, I want to ignore what's already there, and I want to create something which is always the same. So basically, like how would you implement, I don't know, like you can imagine map const unit, right, on a normal list. Like ignore everything that's there and replace everything with a common element. So that does almost work, right? The only thing is that, and oh sorry, I did not want that. The only thing is that basically what you really should think of as an NP of f of xs of is that it is a list where every element is wrapped in an f. Like, so the f is specifying sort of a type constructor that every element in the list is wrapped in. So basically an NP of I is actually an NP of identity. So that means it actually contains exactly the values that we would imagine. But we can also instantiate this f to k, which is a constant type constructor, which basically says, like they're all going to be the same rather than of different types. And so basically, in order to do that here, we have to wrap the unit in a k. And then that works. And then we have an NP, that's the type, the whole. So we have an NP where now every element is wrapped in a k unit. So that means every element is unit. And we want to go from there to an int. And now, because we have a library that has existing functionality, it has a function that is called collapse, which takes a product that is actually of this k form, because that is actually a homogeneous list, and turns it into a homogeneous list, right? So if we have a product where all the elements are wrapped in k, we can call collapse NP on it. And at that point, we have a list of unit. Right, so now we have a normal list of units, and we have to go from that to int, and we can call just a normal length function on it. Okay, and both are doing the same, right? And in this particular case, I guess count args is probably better, or perhaps even better would be to write count args but with an accumulator. But basically, even in this simple example, you can see that in principle, yeah, you can use these sort of higher order functions and traversals in order to manipulate products and sums in nice ways and get good results. So if we try these out, count args on I of var x and I of var y and nil, all right, that gives us 2 because we have a list of length 2, and if I do the same thing with count args prime, hopefully, I'll also get 2. Yes, I do, okay? So that's one ingredient. We can now sort of determine the length of a product. Okay. So the next thing that we might want to do is we want to turn a sum into sort of its index, right? That is similar. And again, we have multiple options of how we can do that. So let me call that, perhaps just call it index, I don't know. So that takes a sum, and S is for sum, and it also computes an int. And again, I mean, sort of the simple way of doing that is if this is a 0, then we just return a 0. And if this is a successor of another sum, then we return 1 plus the index of S. Right, and now let me see if we do, like what was it at the top, like in line 50, you still see successor of 0 of some product, of some list, right? If we just call index on successor of 0 of, and it doesn't really matter because we're not looking at it, so here I can even use undefined, then we get the successor of 0 translated into 1, right? So as expected. So that's the second ingredient. So now, in principle, we have a way to compute the numbers here that occur in encode expression. We can compute the tag number, that's the index, and we can compute, well, I mean, we can compute something from which it is easy to compute the list length, because we can compute the number of arguments, and then the list length is just the number of arguments plus 1. What we still need to do is sort of do the recursive calls, right? And the idea of the recursive calls is the following. So if we have, yes, yes.
Could you maybe show us the definitions of NP and NS?
I can try, yeah. I mean, I'm happy to do that. Let me see. Yeah, this is not a good way of showing them. Let me just write them. Oh yeah, and it shows all the instances as well. So the question, also to repeat the question, was that, like, can I just give the definitions of NP and NS? I mean, the reason I'm hesitating is that I think you should really adopt a style with where you're writing higher order functions on top of them, right? So you don't really want to go to the pattern matching on the constructors very often. But it's nevertheless, I mean, it's a totally valid point. One wants to understand things properly, and in order to understand things properly, you have to see the definitions. So let us briefly give the definitions. So this is the definition of NP. And this is the definition of NS. I'll say something about these in a bit or in a moment. Yeah, now of course I get ambiguous occurrence, so let me comment those out. So NP is easier to understand, I think. NP is really, as I said, it's basically a list structure, right? And the two arguments are, the F is the thing that every element of the list is wrapped in, that you can see nicely in the type of the first argument of the cons constructor. So like the thing that is actually contained there is an F of X, not just in plain X, but an F of X. And then nil is the empty list. So the second parameter of NP basically gives you the type information of all the elements that are in the list, right? And that is a type level list. And so nil is indexed by the empty list because it contains no elements. And cons looks at what is the type of the first element, that, like the head, the first argument of the cons, that's the X. And then it's followed by another heterogeneous list, which has elements of types XS in it. And then the constructed product is indexed by xcons XS, where that is a type level cons, right? So basically, if we look at the type of let's see, I true cons I, what is a good type? Just false, and I 3, or perhaps a character to avoid overloading. Then you get inferred, right, that this is a product of identities of 3 elements, the first being a bool, the second being a maybe bool, and the third being a character, okay? That is a product. And the sum is a little bit harder to understand, perhaps, but the idea is, again, you have a certain number of elements, and you want to choose one, okay? You want to choose one out of several elements. And then the idea is, I can either choose the first, or I can not choose the first, okay? And choosing the first is Z, and not choosing the first is S. And in both cases, we need the knowledge that there is at least one choice. Because if you have 0 elements to choose from, you cannot choose anything. But as soon as you have at least one element, that's why the result types are both x cons x's, you can choose either the first or not the first. And if you're choosing the first, we additionally have this, like basically the payload of the sum. So basically we additionally have an f of x at that point. That is just a choice, it's a design choice. So we say a sum is not just, it's like a generalization of either, right? And a generalization of either to multiple different things. And either in Haskell, you also have either A, B. So you tag it with left or right, but then you also have something at that point, either the A or the B. And similarly here, we also basically have one out of many possible things. And sort of basically the payload is the f of x, which is in the z constructor. And the successor basically just says, okay, we skip over the first possible choice, and then we still need to make a choice in the rest of the elements, and the rest of the elements is one less. So that's why the argument to the S constructor is a sum out of one fewer elements, okay? And yeah, that's the type definitions, and again, we can look at an example. We can basically look at what is the type of, say, successor of 0, of I, of true. And this will be perhaps surprising, perhaps not, because it says it's a sum where sort of the elements are wrapped in I. Well, that is because I said I true, but we haven't given the complete type information, so it's as polymorphic as possible. So it says it's a sum of at least 2 choices, right? Because I picked the one which has the number 1, so there must be at least 2 choices, and we don't care, just by like looking at the type of this particular thing, what the type of the first thing is. So that's a variable, that's x. The second thing better be a bool, because we have an I true in there, and there can be arbitrarily many other choices. That's the excess. Okay? Does that make sense? Okay. Yes, that's a good follow-up. The question was, can I show the type of the representation of expressions? So that is called rep of expr. And I'm using this colon kind bang syntax, which in GHC gives us the kind, and GHCI gives us the kind of the expression, but also if there is a type family involved, computes it, right? And that's what I'm actually interested in here. So here, we're saying the representation of expression is of kind star or type, right? I mean, that doesn't really matter. But then it's a sum of products. SOP stands for sum of products, where the elements are all wrapped in an I. And then basically you have a table, right? It's a 2-dimensional list. Sort of we first have the outer list is a choice, like it's a sum, and within the sum it's a product. So the outer list basically is giving us a choice between 3 different constructors, the first being like the var, the second being the app, and the third being the lam. And then within each of these choices there is a product, and the product is like indexed by the inner lists, because the var contains 1 argument, which is a string. The application contains 2 arguments, which are both expressions, and the lambda contains 2 arguments, of which the first is a string and the second is an expression. Okay? Does that answer your question? Okay. Yes.
What is this type parameter f used? I guess you showed one example.
Yeah. Yeah, so okay, I mean, I'm learning here as well. So I mean, so first of all, the question is, what is the type parameter f used, and can you motivate it better? So So we're falling back into the trap of like following my usual approach of building everything from the ground up, and perhaps it is after all the better approach, because you want to know all these things right now, which is perfectly fine. But I'm slightly worried that in the end we'll again not have time to actually write the encoder and the decoder. but but nevertheless, I mean, these are valid questions, and I should answer them. So what I've just said, so an SOP of F, right, is approximately, because it's new type wrapped, that's why it's approximately. Apart from that, it's exactly, but it's a new type wrapped sum of products of F. And this is the main reason why there is this parameter, because the sum, right, contains in every choice a product. And because you want to exploit that, right, you need or want this parameter. And there are also good reasons to do it for products, because we've already seen that you have such a thing that you want to map all the different things to uniform things, like go from I to K or something like that. So it gives you a lot of power in general. But this is probably the sort of the fundamental reason that in the sum structure you want to exploit the knowledge that you statically know that while you have a choice between different things, they're not completely different, right? They're all products, and that is that you allow to capture here, right? So in particular, SOP of I is an NS of an NP of I, where the inner things are all wrapped in the identity. And if you look at the type of from, it'll give you, like for anything that is in the generic class, a function from A to rep of A. And rep of A, as we've seen, is always an SOP of I of a what's called the code of the data type, which is a list of lists, which is just a table which has, like on the outer list has as many elements as there are constructors, and the inner lists represent all the arguments of the constructors. Okay. More questions? Don't let me discourage you. I'm afraid I said too much. It's good. I mean, I'd rather have these questions than you not asking them. I think it's great. I mean, okay. Yes. Yeah. Go. Yeah, so the question is, like, you would have expected that from is sort of recursive rather than just operating on the top level. And this goes back to, like, it was also your question, I think, about like which of the 100 or 1,000 different generic programming libraries you're choosing. That's a design choice of like what kind of approach you're following. So, and multiple design choices actually, but one of the most essential ones is what do you do with recursion and data types? And that is a very committal choice, right? So in both works, you can either capture recursion, and that leads to approaches that are sort of based on fixed point combinators, or you can try to ignore recursion, and that basically requires you to only go one level deep. It's a slight simplification, but basically you're basically by going only one layer deep, you can then reapply recursively the conversion function the moment you need it, and that basically gives you a relatively straightforward way of dealing with all sorts of weird forms of mutual recursion. Whereas if you're trying to capture recursion, the problem is that, yeah, there are different ways. I mean, that data type can be nicely recursive on itself, like expression is, but there can be, I don't know, nested data types, mutually recursive data types, recursion on sort of higher kinds, and so on and so forth. And then you need to express all these things in some general representation. So just staying away from that is the pragmatic choice. But I mean, certainly in the more distant past, I've I've been more ambitious there. Okay, are we good? Yeah? All right, so let me try to retrace my steps. So where were we? We had written a function that counts the arguments. We had written a function that computes the index. And I was going to show how we can recursively apply encode. So the idea of recursively applying encode, I'm going to show this sort of in isolation first, is the following: recursively apply encode. If we have a product, right, and let's say it's a product of identities in this case, and it has some arguments of some types, then, well, what does encode do? Perhaps let's show that in between. What's the type of encode? It turns an A into an encoding, so it always produces the same result type, regardless of what the argument type is. So I could imagine that I could get from a product of identity of XS to a product of constant encodings of XS by just applying encode in every position, by essentially mapping the encode function over everything, okay? So basically what I want is more or less this. I have a product, and I want to map over that product. And what do I want to map? Well, everything in the original thing is wrapped into an identity, and everything in the resulting thing is wrapped in a constant, and I want to just apply encode to this X. Does that make sense? There will be a type error if I actually, or perhaps there is a type error displayed already, but that might be somewhere else. But there will be a type error with this. Can you see what the type error is conceptually? Like, what have I forgotten in my whole argument? Constrained. Constrained is not bad, and I think that goes back to one of the things that I wanted to mention sooner or later anyway. So the point is, I cannot apply encode on just anything, right? The type of encode says, well, it's from A to encoding, but only if I have serialize on A. And now I have a product where the types in the product are X's, and I'm planning to map over all the things that are in that product. So that only works if all the types that occur in XS are in serialize. Does that make sense? Okay, and that's why, I mean, hopefully, first of all, sorry, yes?
You only have one call site for code, so it has to bind to one of those.
The remark is that I have only one call site to encode, because so it has to bind to one of those. There is some truth to that, but it's nevertheless not true. So I'll try to explain it in a moment. So we now get an error here that there is no instance for serialize A at the point where we're calling encode. So that is exactly the problem. And it also complains about something for map NP again, and we can fix both problems at the same time. So the problem is that the possible fix that GHC suggests here is useless, right? And that is basically your remark, because it says like, okay, just add serialize A, but A is not in scope. Like A is not even in scope. And indeed, I mean, like if it's really mapping over a heterogeneous list, every element of the heterogeneous list is a potentially different type. So it does not make sense to require serialize for any particular type. What we want is we want to require that all the elements in the type level list XS are an instance of the serialize class. And that is what this all constraint does. That is defined as effectively a type family that iterates over the type level list and computes a constraint that contains basically for all the elements in the type level list a serialized constraint. But that alone is also not enough because you have to tell GHC how to propagate the constraint. I mean, so you can build such a constraint, but again, I think that is also related to your question. You need some magic that actually helps GHC to know how to distribute this complicated constraint over this type level list in order to get it applied in the right way. And that is why you cannot use map NP. You have to use CMap NP, which is for constrained map. And you have to explicitly, this is very sad, I wish that wasn't the case, you have to explicitly tell GHC which constraint you mean. And I mean, you could avoid the proxy. Proxy is basically just a way to have an extra argument that you can attach a type to. But now that you have type applications in the surface language, you could omit the proxy. You could basically write CMap in such a way that it's just CMap underscore NP at serialize. The reason I've still kept it in these libraries, and that's something that I generally like, is that a proxy in a type signature tells the user that the user has to expect to provide some extra type information at that place. Whereas if you don't do that, you have to guess or already know or wait for the error message, right? So it's a little bit of additional information. And now let's also look at the...
Is the problem here that we don't have injectivity for all?
Is the problem here that I don't have... injectivity for the all type. I think it is slightly different than that. It is in general the case that GHC assumes that constraints are not injective in some sense, although I'm not even sure whether that is currently, in the way I'm phrasing it, is possibly not well defined. But in general, if you have a sort of a function that depends on a particular constraint, and you have another thing in scope that supplies that constraint, you have to be explicit of passing it on, and that's exactly what kind of is happening here. So if you're looking at the type for CMap NP, right? Basically, what it does is it requires all CXS. That's the line my cursor is on 81. All CXS. So it requires that a constraint C holds for all the elements in a type level list. It wants a proxy for that constraint in order to fix it, and that is basically sort of the point that if you remove that, then the rest of the type signature is not enough for GHC to uniquely infer what C is. So it's not treating the C as being determinable from the rest of the type signature. And it's less clear to me whether that is really true than in some other situations, but it is the choice that GHC makes. And then I think this is an answer to your question, finally. The reason that we don't have to commit to a single type at which we call serialize in the argument to map, encode in the argument to map, is that we have what's called a rank 2 type argument here, which says what we really need to pass is a function that for all choices of type A, we can go from an f of a to a g of a, and the only extra piece of information we are allowed to use here is that we now know that c of a holds, which in this case means we know that serialize of a holds. So that means the function here, this lambda ix to k of encode x, must be polymorphic, right, in the underlying type. It must not make any assumptions about what the x is, and the only extra piece of information it is allowed to use is that the x is serializable, right? And that is satisfied. And that's why it works. And then we can go from an npf of xs to an npg of xs.
So you also generalize over the kind of A. Is that necessary?
So the question is, I also generalize over the kind. You mean the kind that is called K here in the type signature, whether that is necessary. Yes. Yes, it is, because again, I mean, perhaps it is not necessary for products alone, but it is necessary as soon as you consider sums of products, and then it makes sense to do it for products as well, because remember that the sums are, like in the original form, containing products, right? So the sums are indexed by products of something, and so they're and that's already a different kind. So basically, if you're, in the end, if you're iterating over a sum of a product, you typically get constraints of the form that you want in a two-dimensional list of types, that you want all the inner things to be a member of a particular class. So you will write something like all serialize of XSS. And yeah, and that's where you need the kind polymorphism for. But there are other good reasons to have it as well. Yeah. Okay. But you're asking great questions. I don't have to think anymore what I should explain. You're just going to ask it. That's good. So where do I continue? So now we can recursively apply encode to a product. And I think we have almost all the ingredients now to write encode. Let me see. Let's try to plug it somehow together. So what do we want to, can I just write gencode now? Let me just try where I'll fail. So what I want in the end is some sort of generic encoding function where I want to say, okay, if A is in the generic class, I want to be able to go from A to encoding, right? And so how do I do this? Well, let's do this in steps. I mean, I can always simplify and make it more elegant and again. But the first thing, we go from, let me use scoped type variables here. We want to go from X to rep, from A to rep A, which is a SOP of I of code A by applying from. Okay. And then, what do we want to do then? Then we want to, I guess, compute this index, because we need the index. Like we need the tag number, right? So let me actually unwrap, perhaps, let me unwrap the SOP. Then this is an NS of NP of I, right? So now we have X prime, which is a sum of products. And now we can compute the tag, which is just an int, by calling, what did I call this? Index, right? Index on the sum. Index on this, okay? Right, so that's the that's the thing there. And then I want to, in the end, I want to say something. I want to start by encode. Well, okay, so that's perhaps still problematic. So perhaps I need one additional step where or can I do it right now? So I basically want to, so the question is, how do I get rid of the sum structure? So I mean, in a way, I have shown that if I have just a product, I can map everything to a constant type, but I have a sum of products, and I don't really want to do anything with the sum. So perhaps I'm going to write one more helper function that basically says encode sum that gets past the tag on the X prime, and then encode sum should have the type int to ns of np of I of some xss, and from there I want to go to an encoding. So this is the tag, and this is the sum. Yes?
On line 51, this
Yeah.
What does the syntax mean? So what are we defining? So we're defining the representation of text.
So SOP is just a new type. So the real definition is something like new type. SOP is SOP of. So SOP is the constructor of the new type SOP, which is just a sum of product. And the only reason there is this new type is that you sometimes want to define class instances, and class instances you need a new type. Yeah. No. Sorry. Yeah. All right, so what do we have? Encode sum of tag. So basically here we want to use the recursively apply encode that we already have. And basically there is a way to map over an NS as well, right? So just like we can map over an NP. So basically what we can do here is we can use map NS with something on the sum. And then hopefully the result of the map NS will map the NS to something which is also of K of something, right? And because it is of K of something in the end, we can then, of K of encoding, essentially, and then we can collapse the NS. And like if you collapse a product which contains constant types, you get a list. But if you collapse a sum that contains constant types, you just get a single element because it just has one payload. So if the result of the map NS is a K encoding, then collapsing it is just a single encoding, and so that should be fine. And now we again get some problems, but we need to use CMap NS anyway because we already know that that we need to require that. That the inner elements of this list of lists are in the serialized class. So, and here we can answer John's, or like get back to John's question. We really need to say that all of serialize holds for XSS. And here we need to pass on proxy of all serialize. And now I've made a mistake. Oh, because I'm still missing that argument. And oh, the type application is at the wrong place. Yeah, this should be here. Okay, and actually now I'm getting immediately an error up here in the GN code, and it's totally right about that because I mean here I need to do the same thing. I mean it's not enough for the type A to be generic. We also need to know that all the elements that appear in the code are members of the serialized class. Okay, and now we only need to fill in this one hole here, which is going from an NPIA to a K encoding of A, right? And this can use recursively apply encoding, but that's not quite enough, because recursively apply encoding gives us a product of all the recursive encoding types, right? But now we want to concatenate them all, and this goes back to what the original definition does. It basically here we can, let me just try to give me a little bit more space. What we want to do here is really we take this product and at this point we want to create an encoding, and this encoding has the same shape as this thing. We start with the list length. So here we can really write this encode list length of something, concatenated with encode word, I think it is, concatenated with something else. Okay, and so what is the list length? Well, I mean, okay, perhaps the word is easier. The word is the tag that we have been passing to this function. Only that actually the tag is an int and we need a word. So perhaps we should have computed a word up front. For the time being, I'm just going to say from integral here, but we can possibly fix this. And then the right-hand side is sort of the recursive calls to encoding. So that should be recursively apply encode, and that should be P. Let me see. Oh, and okay, and that gives us a product of K's, right? So that should be collapsed, I guess. And then, what's the type error actually saying? Oh yeah, and then collapsing gives us a list of encodings, and if we want to, we basically want to concat, like monoidal concat, or S-concat, semi-group concat is the same, essentially, the recursively applied encoding. Okay, and now the only thing that is missing is the list length, but the list length we have written, so what was it? I forgot the name. Count args? Was it count args? Count args. Okay. Let's do count args on the product, isn't it? No, apparently not. Oh, this is again word versus int. Okay. So another from integral. Okay. So this looks very ugly now. Let me perhaps try to align these things properly. And then see where I guess something like this. Okay. So this is hopefully the complete definition. So let me see if I can plausibly replace. So if we go all the way back up here and remove sort of the generically derived, GHC generically derived serialize, use our own instance for serialize again. And this was sort of using the specific encode expression and decode expression functions. And we said at some point, let's look again with these for comparison. Encode, or serialize is defined in terms of encode and then does something else afterwards. So if we do serialize of our example expression again, then this is what we got before. And I'm going to change this marker here so that it doesn't accidentally get re-evaluated. But I want to, for comparison, I want to now use our generic definition of encode instead. And hopefully, we're getting the same byte string. Is it? Off by one. Off by one. Yes, I even know where, because we did not add 1 to the list length, right? I think that is at least one of the problems. Perhaps there is more. So we should add. Because it's, I mean, the list, the arguments of the constructor plus 1 should be should be the list length that we're encoding. So let's see how that changes things. Okay. Now it's actually the same, right? Yeah, I think so. Good, okay, so that's a success. And of course, I mean, this is why, I mean, of course, this is hard, perhaps feels harder still than it needs to be, but it is also because we've seen many things the first time around, and we've done things in more steps than I would probably actually do them, right? So for example, if we look at GEncode, we don't really need all this let stuff. So, I mean, we can just like dispatch immediately to encode sum of index. I mean, basically we can, I mean, what I would probably do is sort of gencode is unswap. Unswap is just stripping this SOP constructor, and then, I don't know. But well, perhaps it's not even needed. I mean, I can leave it like that. But effectively, yeah, I mean, you can simplify here if you want to. I mean, that's not it's not a big deal. And also encode sum and encode and recursively apply code could conceivably be inlined into encode sum. And you can possibly go even further and say you don't even necessarily need to split the sum and the product structure in the way we're doing, because you can just map over a sum of products in one go. So basically what we've now been doing is we have two map calls, one on the sum and one of the products. But sort of like one of the advantages of having SOP be a type, you can also just map over the SOP as a whole and basically do both these mappings in one go. Okay, so we are at 3:15. We have about 45 minutes left. I think that is enough to do decode. I think I would rather do decode because it is, like, I mean, then it's complete. Than to just try to beautify this function further. But if you would rather see beautifying this function further, I can also do that. Like, who's in favor of doing decode? Okay, good. Any questions about encode? Okay, good. So for decode, we need similar things, but also slightly different things. So actually, the beginning of decode is really simple because it's always the same. Right? So decode always starts with sort of a monadic do, and it always starts with decode list length, and always starts with decoding the tag. And then we kind of have to dispatch on the tag, or the length and the tag. And then we have to do some sort of recursively applying decode. But actually, this recursively applying decode is more interesting than in the encoding case, because it's not just it's not just sort of like mapping everything to a common type and then sort of concatenating the result, but it is building up something of the target type, and it is all in this applicative structure. Right, so that makes it really interesting, and we don't really have an input if you think about it, because, like, I mean, the thing that we're producing is just a decoder. So what we want is basically the following: there is a way to take the structure of the data type, which is, if you like, the sum of product structure, but also if you look at just the code, it's sort of like a two-dimensional table, and to just conjure up a table of decode calls. Right? So whenever there is a function that basically produces a product out of what seems like thin air, but really the type is the input. So if you have a function that is sufficiently polymorphic, or an expression that is sufficiently polymorphic, you can just create a product of things, and because that is reminiscent of sort of the pure in an applicative structure, this function is also called pure in Generics SOP. So let's look at a simple example of this one first. So pure NP. And I want to say create a product of something of type bool, int, char, or something like that. And now, but in order to create something of f bool, f int, f char, I need something that is sufficiently polymorphic. So that it could be an f of bool, an f of int, and an f of char at the same time. And again, sort of like, if you want it to be truly polymorphic, one way to do this is to pick something here for the f, which has a common inhabitant for all these different types. So now, if we do maybe bool, maybe int, maybe char, right? Nothing is an element of all these three types. And indeed, if we pass nothing as an argument to pure MP, then we get just a product of 3 times nothing. Okay? Similarly, we could say we want an NP of lists. Now we have to produce a list of bool, a list of int, and a list of character. But again, the empty list is an element of all 3 types. And funnily enough, you can see that GHC, because it has a special show instance for a list of characters, prints the 3rd one differently. But you get this, right? And just like there is pure NP, there is also C pure NP. And C pure NP is again taking a class constraint, right? And as a class constraint, we could pick a class of our choosing. And so, for example, there is, I don't want to import that now. There is this like slightly controversial library that basically just gives default values of various types. And so we could use this, something like this, proxy default. And then just use def here. And now the difference between pure NP and C pure NP is again that the thing that we are applying to C pure NP can assume that all the types in the product must be now an instance of this default class. And in this case, like we could possibly produce something like I if we just say I def here. And of course, if I call this now, I will get an error message that Boolean is not an instance of default, and if you scroll down, that integer is not an instance of default, and that character is not an instance of default. But if I make them so, if I say instance default bool where def is false, instance default int where def is, shall we do 42 again? Instance default character where def is x. And then I'm going to reevaluate that. Then I'm actually getting, right, the default values for all these things. And this is what I can use in order to produce decode calls all over the place, right? Because essentially what I want is for all the things in my type, I want to call decode. And then I want to continue processing that somehow. So I can use something like, and here I cannot really show that in the end because it's, but I can show the type. I can do something like decode NP proxy serialize, and I can say decode. And then I get an NP of decode S, for example, of Boolean, integer, and character. Decode, not in scope type, decoder. I think this type is called decoder. And decode NP, I did not want to call decode NP, sorry, I'm getting unfocused. Yeah, okay. So I mean, I've already given the type signature, but basically this proves that this is a type correct call, right? I mean, the fact that I'm getting the result back like this. So C pure NP of proxy serialized decode if I have the type information that I want to have a product for a particular thing, it will give me a product of decoders, which, like in every position of the product, I have a call to decode. Now, but that's not all. I need this for all the possible constructors, right? For all the possible constructors, because I don't know which one I want to decode, and possibly I want to decode them all, and I eventually want to wrap them in the different constructor values. So what I can just do, so just like Generics SOP has products and sums of products, that has 1/4 sort of common combination, which is a product of a product, which is essentially a two-dimensional heterogeneous table. And sometimes that is something that you really often want in the context of generic programming. You want to do something for all possible constructors and for all arguments of the constructor. So replace the outer sum with a product as well. And so basically, I can change this example here to be POP for product of products. And then I can put POP here for product of products. And then I can actually put a two-dimensional list here. And I can, like, just to make it more concrete, I can put the one here for which we have for our expression type. I mean, can actually use code expression, right? And and that works, right? So that gives me decode calls for all the different arguments of all the different constructors. So basically now, I want this in the end, where you can think of decode that we have decode expression and decode. That doesn't really matter very much, because the moment you make expression an instance of the serialized class and say decode is equal to decode expression, I mean, then decode and decode expression is the same thing. So basically, what we have now is sort of the table which contains decode for var and decode twice for app and decode twice for lum, but we don't have sort of the constructor names applied to them or the applicative structure, right? And so this is where another useful function comes in, which the Generics SOP library provides, which is called apply injections. And apply injections would possibly be better named constructors, because that's essentially what it does. Because if you look at sort of what is a constructor doing, it's basically injecting arguments into a sum at into a particular position, right? It's making one of the particular choices. And basically what apply injections does, let me try to see if I can just show the type of that. There are different forms of it, but we want this one, I think. It takes such a table, it takes a product of products of things that we already have, and then it basically creates a single product where each element of the product is a sum of products. And how does it create the sum of products from the product of products? Well, by basically injecting into the first constructor for the first row of the table, into the second constructor for the second row of the table, into the third constructor for the third row of the table, and so on. So basically, you get like if the original POP was just the decode calls, what you then get is effectively, right, the decode call tagged with a var, the decode call tagged with an app, and the decode call tagged with a lum. So let's try that. If we can make that work. So let's see. Type of app injections POP. Oh, but perhaps I should go away from the, perhaps I should actually start making an actual definition, because we want that sooner or later. So let's say the decode calls, so we want something like C pure POP of proxy serialize decode. And let's see, what should be the type of this thing? This would be a POP of decoder S of some XSS, but we need to know that all of serialize of XSS holds. So that's the decode calls thing. And now we want to like decode calls injected. I don't know whether that is the right way of doing this or calling this. So we want to call app injections to decode calls. And what should the type of this be? This is the monomorphism restriction, I think, which is causing this type error message, because I'm having a top-level binding without an argument, and it has a class constraint. So I think it could actually, in principle, infer this, but due to the monomorphism restriction, I'm getting this error. So this should be all of serialize XSS, and then it should give us an NP of K of SOP decoder S XSS, XSS. Okay, wow. I mean, possibly you're better off not giving all these intermediate type signatures, right? But for clarity here, that's the thing. So the problem is now that we need to select the right one out of these, and then we want to transform it back into like from an SOP. We have to do two things, right? We have a product of these things. We have to select one element out of these products, but even then we have an SOP of decoder as XSS and not an SOP of I of XSS, right? So we somehow need to like sort of do this applicative wrapping thing, like that everything should be like wrapped in stars and so on and so forth, right? We want to extract out sort of the decoder S to the top level. Basically, at some point we need something that goes from extract decoder, that goes from SOP decoder S XSS to a decoder S of an SOPI XSS. Right? And this is a common pattern. This is not so unlike stuff that we all know from other areas as well. So, for example, if you think of normal lists and you have a list of IOA, but what you really want is an IO of a list of A, right? What do? Sequence. Yeah, I mean, traverse and sequence is not much difference between those two, but yeah, so sequence, right? And so sequence is like, I mean, yeah, sequence exists in Generics SOP as well. And there are actually, again, there are different versions of sequence. There is a general version of sequence. That's this one. Oh no, actually, this is the one that you often need. The simply named one is the one that you need often. That's the one that we need here. That goes from an SOP F to XSS and just extracts the F out and leaves you with an SOP I XSS on the inside. But there is a more general one, which I think is called sequence prime SOP, which basically allows you to pull a part out, right? So if you have an SOP of a composition of F and G of XSS, it pulls the F out and leaves the G in. But you can see that if the G is the identity, then it collapses down to the original form. So here we only need the this one. And actually, this should just be literally sequence SOP. Ah, yes, and okay, we again need some sort of, okay, I never really explained this. I think I need all top accesses. I never really explained this. So this all constraint satisfies two purposes. One is that it actually expresses that all elements of a type level list are a member of a particular type class. But it also serves as a singleton for lists. And yeah, this is a complicated thing, which I won't have time to explain properly today. But sometimes, for certain constructions that you need to do when you're working with type-level stuff in GHC, you need to know slightly more about the structure than the kind itself gives you. So XS is a type-level list, but that doesn't actually tell GHC very much. Basically what a singleton encodes is that what that means in practice is that it actually is either the empty list or a cons and on the type level. And so a singleton sort of tries to establish a correspondence between term level stuff and type level stuff, and sometimes you need a little bit of extra information to conveniently work with these things. And basically this is the reason of such a all top access or all top XSS constraint is sort of to basically just say, oh yeah, and the list must actually be a list, which is a little bit of a vacuous statement. So it's also a constraint that can always be satisfied, but certain functions need it. Yeah, I'm aware this is not an ideal explanation, but I'm slightly worried that if I'm having this explanation right now, I won't be able to finish. So I'm sorry for that. Perhaps we have time in the end. We'll see. Okay, so we have the decode calls. We have the extract decoder. So we're actually almost there. The only thing we need to do is to somehow look up the right element out of the product. Right, and for that, well, basically, I said, like the beginning of the decoder is simple. We start by decoding the list length, we decode the tag, and then basically we have to build a table of some sort where we map tags with elements of this product and or find the right element. I mean, there are really different ways of doing this. We could literally just write a lookup function into the product. That would be one. We could write something like lookup index, given an int and an NP of f of xs would give us a maybe of, and this is really a maybe, I'm going to say it gives us a maybe of an f, oh yeah, well you probably want this to be a k, gives us a maybe of an a. Right, that's one way of doing it. Why is this really a maybe? It's because this is really a lookup that can fail, even in decode, right? We're decoding a tag, and if the serialized string is well formed and has actually been produced by the serialization of a correct value, then it should never fail. But we are reading potentially completely untrusted input, and we could be decoding a negative number, well, not the negative number if it's actually a word, I was slightly imprecise there, but a very large number potentially, and it might perfectly be outside of the range of the number of constructors we have. So we really have to be prepared for failure here, right? So this is, again, this is a direct way of doing this. So we could do lookup index of, I don't know, 0 of x con something of kx con something is just x, and lookup index of I of something cons xs is lookup index of I minus 1 of xs. And then lookup index of anything out of nil is nothing. Okay? So there are like sort of perhaps nicer ways of writing this. So for example, I mean, really, just to show possibilities, not really to make value judgments of what's better. What we could also be doing is we could create another product, right, which contains just the indices of the constructors, right? So another product which is indexed by the same access, but just contains the number 0, 1 up to n, like depending on the number of constructors. Then we could zip the two products. And zip, of course, exists in Generics SOP as well. You can zip two products that have compatible structure together into a product of pairs. And then, because after zipping, it's still sort of a product of constant things, you could collapse that product of pairs into a list of pairs. You could turn that list of pairs into a finite map, and you could just do a lookup into the finite map, right? I mean, again, it's just to show possibilities, right? So these kind of conversions are possible. So you have different styles of programming available, but if you want to do these sort of vast transformations, you can do all that, right? It's all possible. But for the time being, let's be content with lookup index as it is, and let's see if we essentially can just get it done. So let's see what's potentially still missing. So if we can do all, so basically we want to go for generic A, and then all serialize XSS decoder S code A. Expected, oh yeah, rep, no, not code A, right, sorry, okay, A. And basically want to start by do, and then, where was my original decode expr? We want these two things exactly like we had them before. And for simplicity now, I'm going to remove the checking of the list length. I mean, that would be sort of an exercise for afterwards. It's not going to be that much harder anymore because it's just more of the same. It's not a conceptually new thing. But I'm basically just ignoring the length check. I'm going to trust that that one is okay and simply do a dispatch on the tag. And the dispatch on the tag I want to do was I want to do a lookup index of the tag in the product. And which product do I want? That is the decode calls injected product. Decode calls injected. And then this is again int versus word. I got that wrong all the time today, sorry for that. And what is this? What is this type error? Okay, so this is okay. This is saying it cannot yet tell that the call is actually the one for which I've put the class constraint on top because I'm not using the R for anything and because the context doesn't determine yet what I'm using the R at. So hopefully when I'm using the R, this will go away, this error. So what I have here now is I want a decoder SA, and I have R. Can I figure out what the type of R is? R is a maybe of an SOP decoder SXS. So first of all, I have to dispatch on the maybe. So let's see. K is R of nothing. This is actually fail, could not decode, something like this, right? Or it is a just of an R prime. And now I need still a decoder SA, but I have an SOP of a decoder of something. So we had this, what was it called? Or basically I can just use sequence. We had established that it's just sequence, but I had wrapped it in something which was called differently, which I'm no longer finding. Extract decoder. But I mean, basically we have established that it's just sequence. So basically I can do sequence call to R prime here. And I think this is still because the context does not yet determine which type we actually want this at. And now the last step is that we have to go from decoder S, I mean this S0 will be forced to be the same as S in the end, from decoder S of SOP IXSS to decoder SA. And that is just basically the reverse conversion from, right? If you remember, like in the very beginning, we started saying, oh, what the generic class gives you is a way to go from a type to its representation. And of course, you have the other direction as well. You can go back from the representation to the type, and that is taking you back from an SOPI of some XSS to the original type. And so because decoder is a monad and an applicative and a functor, we can map over a decoder, and we can just apply to the inner thing. Okay, and now there's one type error left. Let me see. Yes, so this is actually correct. This was a mistake because, I mean, I required all serialize on XSS, but XSS is actually not in scope, really. What I want is that on a specific XSS, which is the code of A. Okay, and now it type checks. And now we should try it out. We should see whether what happens if I replace this with GDecode. And if I do a deserialize of serialize expression. Oh, and I have to require a result type. Otherwise, it's sort of, I think like in GHCI extended defaulting rules, then it tries to deserialize it as unit, which will fail. I mean, that's understandable. So we want it to be an expression again. And we get the original expression back. So in the... Okay, so that was the goal. And I think, I mean, so at the very least, we succeeded in writing a not entirely trivial generic or pair of generic functions. So why not entirely trivial? I mean, in a way, you can argue that isn't this almost the most trivial function you can write, and it's already that hard. I mean, again, I mean, if you really collapse it down, if you collapse it all down, it's basically, I don't know, 4 lines for the encode and 5 lines for the decode. That's, I mean, so it's not, I don't think it's that hard. But also, it's subtle, right? Because it's often almost what you want, but not precisely what you want, and even sort of small mismatches in the structure create quite a bit of work if you really want to do it in a type-correct way. So for example, this simple thing that, I don't know, right, you have to know the number of the arguments plus 1 before you encode the tag. That creates a little bit of noise, right? Because like conceptually, the tag is the first thing that you determine, and then underneath is the product structure, and from that you can determine the length. But this basically requires you to look at sort of the size of the product structure before, or to push the tag number into the rest of the function, which we did, right? But this sort of stuff creates a little bit more problems, but it's the typical problems that you actually have to solve, and it is actually, despite all the, I would say, like confusing or potentially scary type error messages, it is also very, very good that you get all these type error messages, because it's extremely easy to make mistakes, and they really push you into the right direction. and sort of the trade-off is eventually relatively good. And I mean, I don't really want to play generic programming libraries against each other, in particular because I also like GHC generics and I also worked on GHC generics. But if you compare the code that we have come up with here with the code that is actually in the serialized library for using GHC generics, you will see that it's 3 times as long. So it's like for the same simple thing doing even more work. Okay, so I want to give you the opportunity to ask some questions if you still have any, and I won't get to my other example, but I can still talk about my other example at a high level because I think there is an interesting message to be made. So perhaps we can reserve like 3 minutes for that, but before that, perhaps first give you the opportunity to ask any questions you still want. Yeah, John.
You could probably guess what my question is going to be. You wrote quite a lot of fairly intricate code here, and indeed you made a mistake. The type error didn't catch. You're off by 1 error. So my question is, how do you test this? In particular, you would like to be generating random types, you know, an unbounded potential number of them. Does that mean you have to have a separate run of GFC for each test?
Okay.
Or is there a generic?
Okay, so the question is, how do you test all this? So in particular, John pointed out correctly that I made a mistake that wasn't caught by the type system, namely the off by 1 error. And that fortunately I found it relatively quickly, but in general you might not, so there should be a way to test it. And it's a good question, and it's not an easy to answer question. So yes, I think you could conceivably say you can write a test system which basically randomly generates types even. I mean, it's not completely unrealistic to do this.
And shrinks them. And shrinks them, please.
And shrinks them, yeah. Yeah, I think in practice it's going to be difficult, yeah. So I mean, so in practice, what you probably end up doing is, at least on the type level, you're going to apply some sort of unit testing. Perhaps one can justify that to some extent, right? And I'm actually not completely sure anymore because the history of generic programming is that long. I actually believe there was some work on this. So basically, sometimes you can make arguments along the lines that if you're testing, I guess it's perhaps similar to the kind of thing you can make arguments for parametric functions that if you test them on lists of natural numbers that you're basically doing enough already, right? And there is conceivably a somewhat similar but probably more complicated argument to be made here that if you test a certain number of different data types that you have basically exerted all cases. But I'm not sure. I'm not sure. It's in general a good point, and I think in particular for functions like this, it's not easy to do. My argument, nevertheless, would be like, what are the alternatives, right? The alternatives are either to write encoders and decoders for every individual type, and then you also have to test them for every individual type. And that's something you can certainly do. You can say like the general property that should hold is sort of this kind of round-trip property, and then on all types you're actually using the function, you add the test. I memean, that is something you can still do. So compared to that scenario, I would say this is still a win. And the other option that people are using is use metaprogramming. I mean, basically use untyped template Haskell to generate the whole thing. But that's even worse because now, in a way, you at least have some sort of, at least have the guarantee that the resulting program is type correct. Like with untyped template Haskell, you don't even have that particular guarantee. And again, you can argue, well, if you did things right and if you tested it on a couple of types, then probably it always will be. But it's the same kind of belief, right? And so I don't necessarily see a substantially better alternative, but I completely agree with you that it would be fantastic if one could do this. And I think in general, this is again, unfortunately, one of those cases where potentially like full dependently typed languages are superior to something like Haskell because you can You can treat types even more like values, and you can do computations on types. And when it comes to writing something like a generator for types and a shrinker for types, then the sort of equivalence between types and terms becomes really valuable because you want to do really, really advanced stuff on the type level. But yeah. Perhaps you'll you'll just do it. Yeah. Yes.
So you mentioned that Generics SOP has like performance issues, and probably serialization is not something where you want to have like those performance issues. So my question is, in which cases it's still generally like applicable to use something like Generics SOP?
Right. Right. So the question is about performance, and that like serialization is probably one of those cases where you actually do want to be as performant as possible, and yeah, where generic programming is actually applicable. So my take on it, I mean, first of all, I agree that for a general serialization library and some code you put into the general serialization library for everybody to use, Generics SOP is probably not the right place, because then you're basically forcing everyone to use the slow thing, and possibly not even GHC generics, although it's still better to have a generic solution than no generic solution, but you have to put a little warning tag on. But it's one of the reasons why people are sometimes still jumping to template Haskell, because it promises to do better. And actually, I also want to insert here what I believe is the right solution to this is to use staging, but not in the form of untyped template Haskell, but in the form of typed template Haskell. And there is actually a paper from a few years ago by me and some others, by me and Nick Wu and Matthew Pickering, on staged SOP, which is essentially the same, only that you can stage annotate things, that you can basically say, you can guarantee that certain things happen at compile time. And if you look at the decoder, for example, just look at the decoder, right? It's a good, or perhaps even the concrete instance here, right? All this stuff that happens on the right of the case statement and on the right-hand side, right? Like computing this structure, like the var dollar decode, the app dollar decode expression star decode, does not depend on the input. So in a way, like the way we translate this to our thing, all these function calls that we've defined, where was it? And decode calls injected, does not depend on the input. Like they could be completely reduced at compile time, right? Like all the product structure and so on, like the app injections, all these calls, right? There's no reason, they're recursive functions, and GHC won't inline them and won't unfold them at compile time, but there's no reason to. There is no, everything is static. It's all known, right? So basically getting back to the same structure that you have literally for the concrete instance of the code expression should be possible, right? And with staged SOP, in principle, you can. The big problem is that the type template Haskell implementation in GHC has a flaw when it comes to dealing with type classes, and unfortunately, Generics SOP needs rather complicated type class constraints. And despite the staged SOP paper being 3 years old and us having had a local prototype at the time, which basically demonstrated that it could be done, we still have not managed to find the time and energy to put a production-ready version of this into mainline GHC. That is really, really sad, because I feel like that is really the best solution, because you can write generic programs in this style with the same level of type safety, and the runtime performance problem is almost completely solved. You can basically guarantee you get the same code that you would have written by hand, and that's perfect. Compile time performance is still a problem potentially, but the runtime performance problem at least is completely solved. Otherwise, though, I would say in my applications, I'm still using a lot of generic programming, also in client programs. And this goes back to the other example that I was mentioning. So there is a lot of stuff where performance does not actually matter all that much. And correctness and clarity, I mean, clarity in a certain sense is better. And so often, for example, I mean, so the example that I was going to show is still is a little bit contrived, but is derived from something that I have in a real client project. And that is the following. Often you have types that you want to put into some relation to some external representation. So for example, consider you have an enumeration type that lists different options, but the constructors as you label them in Haskell, the constructor names as you label them in Haskell are not necessarily the externally visible names, and perhaps you don't even want that to be, because perhaps the externally visible names are not in English, but you want your code to be in English. Perhaps the external visible names contain weird characters that are not even syntactically allowed on the Haskell side. And perhaps you have other things that you have some of the constructors that you don't actually want to be externally visible, but you might still have a lot of these types, of a particular class of types. So like an application area of generic programming is, in my opinion, exactly this. Whenever you have a certain number of data types in your program that have a certain common structure or commonality, it's not always so all or nothing that you can write a generic function only if you want to have exactly the same functionality for serialize for all data types. You can identify a certain subclass, such as enumeration types, or types where every constructor has exactly one field, or types where you have exactly 3 constructors where the first argument is always an int, or something like that. And then you have a couple of these types, and then you write a generic function for these kinds of types, and then you can exploit sort of common structure. So for example, why the externally visible names are so interesting is perhaps they appear in multiple places. Perhaps they appear in your JSON representation. Perhaps they appear in your HTTP requests in the form of flags. Perhaps they appear in the documentation or something else. So we have various different class instances, something like from row to row from Postgres, something like from JSON to JSON, from ASON, something like from HTTP, whatever thing, and so on. And they should all use the same sort of label mapping, right? And one of the nice things is that with generic programming, you can basically guarantee that like a certain number of class instances are all consistent with each other, because you all go through some sort of common representation and a common function. And I think in many of these cases, the performance is absolutely uncritical, because it's not as like serialization is an interesting special case, and sometimes serialization is also uncritical, but sometimes you have situations where you really want to serialize as much as possible or deserialize as much as possible. But with these other things, it's very often, it's not a big deal whether something takes sort of like a few milliseconds more or less, and just having sort of the consistency guarantees outweighs it. And also because it makes the design more precise and more easy to modify, right? So if it's so nice if you, like for example in this application that I'm talking about, if I want to change any of these externally visible labels, or if I want to change any of the internally visible constructors, there's one place where I have to adapt the mapping, and I can be absolutely sure that it is like automatically carried over to everything. And yeah, so that's the best answer I can give to this. I mean, you have to decide on a case-by-case basis. But it's also, right, basically the other side of it is I think there are more application areas to generic programming than people typically realize. It's not just sort of the author of a library that implements one function for everyone else to use, which probably should hold up to sort of very high performance standards. It is also like the application writers themselves. For your concrete application, you may just benefit from generic programming, because generic programming is not always sort of fully generic or not, but there's a lot of value to be gained, like if you actually learn this skill to write your own generic functions, variants of generic functions, right? I mean, variants of generic functions is a big deal because often you want something that is almost like a derivable thing, but not quite. And like if you can do it yourself in a few minutes, that's really, really powerful, right? Whereas like sending a pull request to the author, would you consider making your function more general or modifying it so that it covers my use case, and then wait for 3 months until that is accepted or something like that? It's much harder. But yeah, it's a trade-off, unfortunately. And hopefully with staging, eventually, a large part of that trade-off will be removed. I'm definitely hoping for that. Yeah. Okay, one final question? No? Okay, then thank you very much.